Good day, ladies and gentlemen. We are back again together. All right, so I'm still continuing on that, Gauteng Prelim paper. Okay, just to show you how you should have actually answered. But it doesn't matter which province you're from in South Africa or anywhere around the world, the principles in physics are all the same. So yeah, if you haven't subscribed, please join our channel and become part of the bigger, broader family. We are growing and we intend to do so. Please don't forget to hit that like button as well after you've watched the lesson and you find it valuable. Okay. And by the way, even for those of you who need assistance with mathematics or physics, please, 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 or even chemistry for that matter, okay, please just send me that email at info@mlungisi.co.za. All right, so I'm taking question 3 of the Gauteng paper. Okay, and it says a boy standing. So this is based essentially on projectile motion, right? Vertical projectile motion. Okay, so they say a boy is standing on a bridge, okay, that projects a ball A. So we've got ball A that's vertically upwards with an initial velocity of 5 meters per second. Okay, so there's ball A over there. Okay, 5 meters per second. And we've got, they say the height of the bridge is 20 meters and we need to ignore the effects of air resistance. Now remember, once they say ignore the effects of air resistance, it means only gravity will actually be acting as soon as we release it, right? Okay, they say give the magnitude and direction of the acceleration of ball A as it leaves the boy's hand. Remember, the moment that the boy, lets go of it, remember in this case that it becomes under projectile motion, right? So in this case, we know that the answer to that is acceleration is 9.8 meters per second squared. Okay, so that's our answer for the first one. Oh, by the way, that has to be downwards, okay, because they did say magnitude and direction, right? Okay, so they say calculate the total time it will take ball A to reach the road. Okay, so the road is down there, right? Now, I'm going to actually do this, if you don't mind. I'm going to try and redraw that so that, so in this case, there's the road there. So we're releasing ball A from that position over there. Okay, so there's our ball A, goes up, and then it means that ball A must have actually, right, there it hits the ground over there, which is the road. So we know, I'm going to just say, okay, let's call this position here position P. I'm going to call that position Q. I'm going to call that position R, which is the point when it returns or it passes the same point again. Okay, and let's call that T. Okay, so in this case, for ball A, they wanted me to find out how long it will take for it to go to reach the ground. Now, what am I going to do? I'm going to take information from P to T. This is the total time of flight. Okay, so if I take information from P to T, let me write it over there. So if I take information from P to T, what is my initial velocity? Now, the most important thing, ladies and gents, please remember to always choose a direction as positive. So I'm going to take upwards as my positive direction. There's nothing wrong. You could have taken downwards. You still reach the same position or the same answer, right? So in this case, initial velocity, right? Remember, it means P is my starting point, T is my end point. All right, so my initial velocity there, all right, is going to be that was 5 meters per second, so it's going to be positive 5 meters per second. Final velocity when it gets to the ground there, please remember we don't know that velocity because we're talking about the velocity or the speed just before it hits the ground, because once it touches the ground, it is no longer under projectile motion, right? Why is that? Because now the ground also exerts a force. And remember, when we talk about projectile motion or vertical projectile motion, we're talking about only gravity being the only force that influences the motion, right? So in this case, we don't know what final velocity is just before it touches the ground there. But what is our gravitational acceleration? Remember, in this case, we chose up as positive, and gravity at any given point in the motion of this ball is always acting vertically downwards. So this will be minus, remember we took up as positive, gravity is acting downwards. So this is going to be minus 9.8 meters per second squared. And we want to find out the time. We don't know the time. And in this case, what is our displacement? And remember, ladies and gents, displacement is the straight line change in position from the beginning to the end point. So where's my beginning? That's my beginning. And where's my end point? That's the end point. So the question is, in a straight line, how far is it from my beginning to my end point? Yeah, I know some of you are thinking, oh, but say this thing went upwards first. So remember, when we talk about displacement, think about it. When it went up and then came back to the same position, what would be the total displacement between P and R? Of course, the total displacement would be 0, because let's just say, for argument's sake, it went 5 meters up, but it went 5 meters down again. So this would be positive 5, negative 5, and so it means that the total displacement between P and R is 0, right? So therefore, the total displacement between P and T would just be that from there, which is 20 meters, right? But remember, it was displaced 20 meters down. We took up as positive, so this should be minus 20 meters. I hope that makes sense to everyone. Of course, I've dragged this. It's just for 4 marks, okay? But I really want you to understand and follow, right? So now we want to calculate the time. So look at this. We've got all of those. Okay, we want time. We don't have final velocity. So what we're going to do is just simply say delta y. This is going to be vi delta t plus 1 over 2 times a delta t squared. Now you may wonder why I picked this formula. This is because we didn't have final velocity, right? So this is the only formula without final velocity, and we're looking for time. Okay, so I'm going to say this is minus 20, which is initial velocity. That's 5. Okay, multiplied by delta t. Okay, plus 1 over 2 minus 9.8, and that's 20. Sorry, delta t squared. Sorry about that. Okay, so just to try and solve that, so we've got a quadratic equation there. Okay, this is 5 delta t minus 4.9 delta t squared. This is equal to minus 20. If we just put that as a quadratic, if we take it to the other side, it becomes 4.9 delta t squared. Okay, you can just call it t squared, right? T squared minus 5 delta t, okay, minus 20, okay, and this is equal to 0. Okay, right, so having taken everything to the other side, now you're left with the mean quadratic there. And please remember, all that you simply do when you want to solve that, of course, you can't factorize there. So I'm just going to take the quadratic formula. That's minus b plus minus the square root of b squared minus 4ac, okay, divided by 2a. Okay, so let's substitute. So that's minus b, so that's minus a minus 5, okay, minus a negative 5, plus minus the square root of, now let's take that, so that's minus 5 squared minus 4 a, that's 4.9, okay, and our c is negative 20 meters. Okay, right, so there it is there, divided by 2 times A, and 2 times A is 4.9. Okay, right, and what is our answer? Okay, I get an answer of 2.59. So first one, delta T is 2.59 seconds. Okay, let's check the other one. Or delta T is equal to, okay, so I get minus 1.57 seconds. Now, obviously, this answer here would not be applicable, right? Okay, why is that? Because, of course, we can never have negative time. I wish we could have negative time, because that would mean we'd go back in time. So the only valid answer here would be 2.59 seconds, right? Okay, so we know that the time it took for ball A to land on the road would have been 2.59 seconds. Okay, swiftly let us move along. Just going to drag this over to this side. Okay, now they say to us at the same instant. Now that's very important, right? Okay, because they tell us at the same instant, ball A is thrown upwards from the top of a bridge. Another ball B, this guy here, is projected up the road. Okay, up from the road rather. Ball B has an initial velocity of 14 meters per second. Now they say calculate how far apart ball A and ball B will be after 1.2 seconds. Now, quite important. Okay, so we've got ball A and ball B and the time between them. Remember that they told us that they were released at the same instant, right? So in this case, we want to know how far they will be from each other. Okay, so let's say they'll be, okay, let's say ball A, just for argument's sake, let's say ball A after 2.5 or 1.2 seconds is somewhere there. Okay, let's call that position X. Okay, and let's say ball B after that 1.2 seconds is at position Y, right? So remember, it would have taken the same amount of time for A to reach point X as well as for B to reach point Y. All right, so we want to know how far point X is from point Y. Okay, right, so now let's do this. Let's calculate, all right, the displacement of ball A. Okay, let's do that first after 1.2 seconds. So I'm going to say this is information for A. Okay, from which point? From P. You remember we called this point P. We said this is Q. Okay, so this is for point A, from P to point X. Okay, so initial velocity, once again, we said that's 5. That's at point P. Okay, final velocity, we don't know anything about point X. We know gravitational acceleration, that's minus 9.8. The time that it took, they said 1.2 seconds, right? And we're looking for its displacement. So which equation of motion am I going to use? Once again, I'm looking for displacement. I don't have final velocity, so I'm still going to use the same formula, delta y. Okay, if you don't mind, I'm just going to work over here. So delta y, that's vi delta t plus 1 over 2 a delta t squared. Okay, right, so now I'm looking for displacement. Let's substitute. I know this is 5 into 1.2 plus 1 over 2 times minus 9.8 into 1.2 all squared. Okay, so that's squared there. Okay, sorry, I'm just trying to squeeze everything in there. Okay, and sorry for that ugly handwriting. Okay, right, so in this case, what do we get? Okay, I get an answer of 0.44 meters. And please note, I get a positive displacement. What does that mean? It means ball P is actually still above the point of departure there. Okay, so it means it's 1.44 meters above, the point of projection. Okay, it was displaced upwards at that point. Right, now let's look at ball B. Okay, now we're talking about ball B from the moment it left the road up until point Y. So we are looking at, remember we had called this, so PQR. So we had called PQR, well, I called it T. Someone doesn't know their letters of the alphabet, eh? Right, so this is point T. So this is between T and Y, isn't it? Okay, so I'm going to say this is T to Y. Okay, what is my initial velocity? So that's when it was from the ground there. Okay, look, ladies and gents, and I always like going through this whole rabble of things. Why? So that it can actually help you, to see what information belongs where. Okay, I go through this rigor so that you can always separate your information. You don't find yourself using the wrong information in the wrong instance, right? So our initial velocity, remember, it's going upwards. We said up is positive, so that's positive 14. Final velocity, meaning at point Y, we don't know what that velocity is, but we know gravitational acceleration is minus 9.8. We know the time is 1.2 seconds. Okay, and we are looking for displacement for ball B, and we're going to do the same thing. So this is going to be delta Y again. That's VI delta T plus 1 over 2A delta T squared. Okay, so let's substitute there. I'm looking for delta Y. Okay, this is going to be my initial velocity. That's 14 times 1.2 plus 1 over 2. A is minus 9.8. Okay, into 1.2. Remember, this is squared. Okay, and what do we get? 9.74 meters. Okay, all right, so now, so it means ball B was also displaced upwards by 9.74 meters. Right, so now we need to find out how far the balls are from each other. Now I want you to think of it. Okay, remember this displacement here, or rather this distance here, is 20 meters. Okay, this one has been displaced what? 9.74 meters. So in this case, from that position, it's going to be 20 minus that 9.47. Okay, right? So I'm looking at point X being, sorry, not point X, rather. I'm looking at point P, being from where we threw it from, right? This is the top of the bridge. Okay, so meaning it's 20 meters minus that 9.74 gives us the distance to the top of the bridge. Okay, so if we take that, we're going to say 20 minus 9.74. Okay, we get 10.26. That's the distance between the top of the bridge as well as the position Y of that ball there. I hope that makes sense, ladies and gents. But remember, we're looking for the distance where it is from X. Okay, in this case, we're looking for, remember, ball A was displaced that 0.44. Okay, I'm sure you can see it now. Okay, so it's going to be that 20, okay, minus this distance 9.74, okay, but I'm going to add that distance there. Okay, yeah, I know it doesn't look really nice. Okay, so this is the 20 meters. All right, ball B traveled 9.74 rather. Sorry about that. Okay, so that's 9.74. Okay, so it means we've got that difference there. But remember, ball A traveled, it was 0.44 meters above that highest point, right? Or rather the height of the bridge. So in this case, the distance that they are apart will be, sorry, from that point there where X is up until that point there, we said there's X there and there's Y there. So it's going to be that 9.74 minus 20 minus 9.74 added to that, so 0 plus 0.44, and the total distance there should be, okay, so they wanted to know how far, so the distance between A to B should be equal to 10.7 meters. Okay, right, so that is how the cookie crumbles. All right, and the last portion of it, they say draw a velocity time sketch for the motion of ball A from the time it is projected. Okay, so how are we going to do that? I'm just going to move this upwards a little bit just to create some space. Okay, so remember that velocity is a vector quantity, right? So it means there must be both positive and negative side. So this is time in seconds. Remember to label your graph. This is velocity in meters per second, right? Okay, so in this case, what happened to ball A? Okay, remember ball A was projected 5 meters per second upwards. So it started going up and it decreased in velocity until it got to 0. So you'd have something like this, starting at positive 5, okay, decreasing in velocity until it gets to 0. This is when it was at maximum height, right? And then they said from the time it's projected from the bridge until it rebounds to a maximum height, okay. Oh, okay. I missed a statement there. They said tennis ball A hits the road below, stays in contact with the road for 0.2 seconds before it bounces up with a velocity of 14 meters per second. Okay, so there's our ball A. Okay, gets in contact with the road, okay, and then bounces up again. So we need to represent that. So they said, so we are drawing a graph, right, from the time it is projected from the bridge. So this is from 5 meters per second until it gets to maximum height. So if you think about it, from it being projected until it gets to that point, the velocity is positive and decreasing rather. Okay, and then what happens? Then the velocity starts becoming negative, right? Because it's going down there. So in this case, remember, a velocity time graph is a straight line. And by the way, if you don't understand what I'm talking about, please go and watch my other videos on projectile motion. Okay, they'll help you quite a lot in developing the theory here, right? So now we said, well, it gets to the ground. I'm not sure, did we calculate the velocity with which it lands on the ground? I don't think we did. That's ball A, right? Yeah, we didn't. So we don't know what that velocity is. Okay, but we know there'll be a time delay a bit. remember when it gets to the ground, so this is when it leaves the height, it goes down, it gets to the ground. Just before it hits the ground, it bounces, reaches another maximum height again, right? So they said there's a 2-second delay, but now remember when it leaves the ground at a high speed, right? So they said the speed with which it leaves the ground is 14 meters per second. Okay, remember that. Okay, they say it bounces at 40 meters per second. And now whatever time it took to get to the ground, and remember, what was that time? It got to the ground after 2.59 seconds, right? So if that's my time, 2.59, okay, what will be the time with which it leaves the ground? Of course, it will be 0.2 seconds later, because that's what they said. So 2.59 plus 0.2, this will be 2.79. Okay, this is the time when it leaves the ground. And I know that velocity will be 14. Okay, so think about it, it's going up, and we said up is positive. Okay, and what happens? Obviously, it will decrease until it reaches that maximum height. Okay, yes, they said until it reaches the maximum height. So this is what our graph would sort of look like. Okay, right, and they said indicate the following: the initial velocity of the ball, there it is, it's 5. The time when the ball hits the road and is in contact with the road, this is the time, that's 2.59. And they said the velocity of the ball when it rebounds from the road, okay, the velocity was 14 meters per second, and obviously decreased until 0. Okay, and that is it. That's your 16 marks in the bag. All right, so I hope that you enjoyed that lesson. Okay, by the way, please don't forget to subscribe, and please tell more people about these lessons that you are receiving. Please don't be selfish. Hi. Okay, right, so I'll see you guys next time. Otherwise, sharp, sharp.